Welcome everyone to our latest InterMET.digital webinar. I'm Dr. Jan Dutton, the CEO of Prescient Weather, the creators of the World Climate Service seasonal and subseasonal forecast application. In today's webinar, we're going to talk about the science and applications of subseasonal forecasting, which is the same as long-range forecasting, with a particular focus on applications in the Asian region. Joining me today are four expert panelists: Dr. Nachiketa Acharya, Dr. Thea Turkington, John Davis, and Dr. Mary Beth Arcodia. To start the session and lay the groundwork, I'm going to present a brief slide and just talk about the emergence of subseasonal forecasts. What I'm showing here is recent headlines from American Meteorological Society journals that focus on subseasonal forecasting. Each title shown has the word subseasonal forecasting in it, and it's just used to show that subseasonal forecasting is becoming more popular. The first reference to subseasonal forecasting in the title is in 1987, and we can actually count the number of times subseasonal forecast shows up in the journal titles. And if we look in 2005, there were 42 titles that included the word subseasonal. And fast forward to 2020, there's 261 titles of articles in American Meteorological Society journals that include the title subseasonal. And so we see the topic of subseasonal and subseasonal forecasting is increasing in popularity, with the number of publications almost doubling every 5 years. So subseasonal forecasting is emerging as a popular topic in terms of scientific pursuit, but it's also a popular topic in terms of the opportunities for the future and trying to solve some of the forecasting problems that we have. The science of subseasonal forecasts is rapidly emerging as a means to provide valuable environmental forecasts weeks into the future, whereas the useful skill of traditional deterministic weather forecasting is limited to 14-day lead times or less. Probabilistic subseasonal forecasts provide users the opportunity to extend the useful lead time beyond the limit of deterministic forecasts. Subseasonal forecasts are being applied in novel ways in industries such as energy, agriculture, and logistics, and also play a critical role in climate change adaptation and resilience. So without further ado, I'm going to introduce the first panelist, Dr. Nachiketa Acharya. Nachiketa is a CIRES University of Colorado Research Scientist 3, working with NOAA's Earth System Research Laboratories Physical Science Laboratory. By training, he is a statistical climatologist with specialties in statistical and machine learning modeling in climate science, especially subseasonal and seasonal climate forecasting. He has previously held positions at the Department of Meteorology and Atmospheric Sciences at the Pennsylvania State University, the International Research Institute for Climate and Society at Columbia University, the Institute for Sustainable Cities at the City University of New York, the National Center for Medium Range Weather Forecasting in India, at the Indian Institute of Technology in Delhi. He received his PhD in statistics from Utkal University in India in 2014, focusing on statistical techniques for extended range prediction of the Indian monsoon. He is actively engaged in several regional climate outlook forums and is co-leading the building block 3 of the Regional Information for Society of the WCRP. Nachiketa, the floor is yours.
Yeah, thank you, Ian, and thanks the organizer for giving us this platform for discussing a very important issue, which we are, as a scientist, struggling for a decade. So here I'm going to present my experience on subseasonal forecast for southeast monsoon over Indian subcontinent, and the approach I took is research to operation to research approach. Just give an idea like where the applications of S2S forecast is important to the stakeholders. And it used to be a term as extended range forecast since it started. Now it's become subseasonal to seasonal forecast. So it has a huge importance because it's between two different time scale. One is like weather to medium forecast and long range forecast. So it's important to have those kind of information to have any planning for either agriculture or hydrology or energy. But unfortunately, the skill of this part is not so encourageable because this is a kind of a subjective map. In the x-axis is the days to, like first 1 day to 90 days, and y-axis is a different skill level of different forecast. And we see like the skill between weekly, like 10 days to 30 days, that time is really challengeable. And that's also need to improve the science and also to understand after the research how to use it in operation, and also get the feedback from the stakeholders for different sectors to improve the products and improve the dissemination of this kind of forecast. So each forecast of any scale has their predictability, and this predictability for subseasonal forecast comes from a wave called Medellin oscillation. And I hope like other panelists will cover it, but just to know, like, this is really connected with this oscillation, and we always talking about opportunity of forecast whenever this signal is very high. And there's a different way to make this kind of forecast. If you think about our tools, the simple tools is the statistical model where you have a time series data and you can just forecast it, or this teleconnection of MJO and rainfall, you can just use a regression based forecast. But unfortunately, those statistical model is limited with their autocorrelation function is poor, or the relationship between different predictors and predictor is going to change because we are in the phase of climate change. So that's what, like, it doesn't work. So we have to depends on the dynamical model, which is a physical science or physical process but model, including all the informations which need to mimic the atmosphere. So that's what, like, dynamical model is so important for this part. But we also need to have a correction of the dynamical model because it's based on different assumptions. On that note, I want to start like what I have been done on this scale. And we are lucky to have a project which is funded by NOAA since I think in 2017 or 2016, where I was a part of Columbia University. We call IRAP, which is International Research Application Program. And after IRAP, there's a different focus region, and one focus region is India. And mostly when you say the India is like huge country, so we took up a state called Bihar because it's a very climate sensitive state. The northern part of Bihar is vulnerable for the flood, whether the southern part is actually a drought prone. So we took this region for a case study, whether we can actually achieve some kind of information, some kind of opportunity by giving the subseasonal focus information to the farmers. So that's the way we started this project. And we took, after long research, we took the 2018 monsoon as a real-time experimental case study. And I'm going to show those kind of things. But before that, just to know, like, whether it is achievable, like whether we can predict this subseasonal, because I explained it's very tough to reach the predictability or prediction skill. So before that, we started research and we found like one example, like, for example, I think 13 to 19 July in 2013, there is a huge break of rainfall between the monsoon region, and we look at different kind of model and we choose ECMWF, which is the best model in this scale. And we found like there is opportunity, although the magnitude is hard to achieve, but at least we can get the signal up to week 4. So from there, we started looking at whether it's achievable, a realistic dream to kind of making that kind of forecast. As I said, like, this climate model has a lot of assumptions. So we need to do some kind of calibration, and we do statistical calibration technique called canonical correlation analysis for that. I'm not going to go in detail, but that's kind of a thing we add top of the raw forecast of climate forecast system version 2. And we use it such a way. So it has a 17-week weekly forecast during June 7 to September 27. We started making this forecast with Indian Meteorological Department, and we kind of make the forecast, put in a website, and also write a text. And we send this text to the agriculture university of this region. They have 2 agriculture university for 2 different region, and they also add their value added information and their experience, and we translate in the local language Hindi, and we send to this text message to the NGOs, which is non-government organization people, and ultimately goes to the farmer. But this is like an example like how we make this forecast. But one thing missing in this flowchart is like the capacity building of the trainers. Like, for example, whoever getting this information at the end before the farmer, whether they can interpret the forecast properly. So we do a lot of training in between. So it has like a 5 years project. So that's what we choose the last year for a experimental forecasting. And 2018 forecast is 2018 monsoon is really bad in terms of on a lot of like 11 out of 18 weeks is actually registered as a deficit. So it's actually bad monsoon. And this is one of the example when you prepare this week 1, week 2, and week 3 forecast. But here I just put week 1 and week 2 and how we validate it with the Indian meteorological data in real time. And ultimately, we do this impact and assessment with the help of our collaborator, University of Arizona and RIMES Bangkok. We actually go different group of the farmers who get the only text, who get the text and the training, and who just get only training and do a lot of economic and assessment of this thing. And we have a lot of meeting after the monsoon. So on that also we kind of published the science of this whole system, and also there's a lot of media report. These are report of the scientific report, like scientific report So that's kind of they cover and they kind of go for each and every farmers to have the interview and how benefit this thing. And I'm so happy because after this exercise, InterMET department actually took it and then they kind of continue this kind of district-based subseasonal forecast. On that note, I just want to mention that what is the future? The future is like the machine learning, which our panelist, Mary Beth, will cover. But I used to want to know, like 2 years back, ECMW have started looking whether the machine learning or artificial intelligence have any benefit to use it as a calibration method to improve the forecast. And I was thinking like, well, I am a PhD student. I was working on that long back, and that time it was not a buzzword like this. And I was thinking like, okay, we can revive this whole method and making a probabilistic approach. That's what we use a neural network and make it like such a way that it produces the probability forecast. And as like any kind of machine learning is hard to achievable in terms of programming, we also make some kind of tools which can be easily transferred to the climate survey scientists so that they can run this tool and make this kind of machine learning plus dynamical model forecast. And as I'm a part of different, RCOPS, which is Regional Climate Outlook Forum, we started making this kind of tool-based, AI plus dynamical model-based forecast in real time. This is an example of forecast in monsoon 2022. We prepared the forecast, we make this kind of, skill assessment and present it to the WMO forum. On that note, I want to just conclude that we explored the S2S real-time forecast which can help to the stakeholders to the agriculture, and the interpretable machine learning is the future, and we should use this technique such a way to actually help for the stakeholders. Thank you.
Thank you very much, Nachiketa. That was very interesting, and I hope it'll stimulate some conversation after all of the presentations. So now I'm going to introduce you to our next expert, Dr. Thea Turkington. Thea is currently the head of subseasonal and seasonal prediction for the Meteorological Service in Singapore. With a background in various weather and climate timescales, Thea has worked as a weather forecaster in New Zealand, before shifting her focus to climate. In 2016, she obtained her PhD from the University of Twente in the Netherlands on the topic of climate change and natural hazards. Her current research work includes working with users to develop subseasonal and seasonal predictions for Singapore and Southeast Asia, as well as underlying research in understanding the effects and impacts of weather and climate processes. Thea, it's your turn.
Great, thank you very much. Just get myself set up here. Okay, hopefully you can see my screen. Thanks for having me. So Nachi gave a nice introduction to subseasonal, so I'll just dive right into this and particularly looking at, can we use this information set for disasters? So we know disasters such as flood, they have a huge impact on Southeast Asia, on property, livelihoods, and lives. Observations, weather forecasts, these are key in disaster management, especially for those critical decisions like, evacuation. But if we're looking a little bit longer timescales, the theme of this webinar is subseasonal. So if we look a few weeks in advance, can we see hints of upcoming extreme meteorological events? So as Jan said, I'm Thea from Meteorological Service Singapore, which hosts the ASEAN, which is the Association of Southeast Asian Nations Specialized Meteorological Center. And these next few minutes, I'll take you through a brief walkthrough of unlocking subseasonal forecasts for disaster risk reduction in Southeast Asia. But first, I'd like to welcome you to Southeast Asia. On the left-hand side, for those of you who are not familiar, this is a map of the area we consider Southeast Asia, and it's showing that most of the region experiences an equatorial or tropical climate. That's what the red is sort of standing for there. For Southeast Asia, actually, weather forecasts typically have really poor skill beyond 7 days. We're not even getting out to that 2-week timescale. However, if we're looking at subseasonal forecasts, as we heard before, we're talking weekly values and we're talking about with a probabilistic sense. Southeast Asia is a region of relatively high skill. And when we consider disasters, in 2020 alone, there were over 500 reported disasters, over which more than 80% were related to heavy rain or storms. So this is a good region to check out the application of subseasonal outlooks for disasters, or more specifically, hydrometeorological disasters. So to demonstrate this, I thought it would be perhaps more useful to go through a case study from 2020. So this will be a quick look through 2 of the outlooks that the ASEAN Specialized Meteorological Center provided before this week of interest to 27th July, 2nd of August. So perhaps you can also see if you can pick where you think the disasters, if any, might occur. So let's start with a plot here showing the chance of very heavy rainfall. So this is showing the probability of exceeding the 90th percentile for rainfall. And it's for that week of interest, so the 27th of July to 2nd of August. And this was initialized on July 9th, so around 3 weeks before. You can see here there's an increased chance of rainfall over parts of eastern Indonesia, so it's more than 3 times the usual chance. The model's also predicting an increased chance over southern parts of Thailand and Vietnam. Although including other information, so this is including the skill of this product, looking at climate drivers, like Nachi talked about the NJO. The outlook we actually provided was a small increased chance of very heavy rainfall in eastern Indonesia. And we specified for those who have excellent geography of Southeast Asia, northern Sulawesi and to northern Papua. Moving forward 2 weeks, looking at the run with initial conditions now from the 23rd of July, we see the model is much more confident for that part of eastern Indonesia, now predicting more than a 70% chance of exceeding the 90th percentile. Looking elsewhere, we can also see an increase in chance over the Western Maritime Continent, and there's also a few dots you might be able to pick out over mainland Southeast Asia, including northern Thailand and parts of Myanmar, but these are very just like single group points, isolated points. So in this instance, given the skill and the climate drivers, we predicted a moderate increased chance of very heavy rainfall in the eastern Indonesia region, northern Sulawesi to West Papua, and a small increase for southern Thailand. So what happens? First, we'll start by looking at rainfall. Here we're showing rainfall anomalies or the different from the average conditions. Now, this doesn't necessarily say how extreme it is and to do with the percentile, but generally speaking, when you see the green or blue, this is wetter than average and the reds are drier than average. So doing sort of a rough eyeball comparison between this observed rainfall and the outlooks, we can see most of the areas with an increased chance, at least at that week 1 plot, match with the areas that are wetter. Although there are some areas that were wetter, observed to be wetter than average, but we didn't really see that increased chance in our outlook. And this includes the Philippines and parts of mainland Southeast Asia, particularly Laos, PER. But of course, the question we're asking are, where did the disasters occur? This figure here are showing the general areas where disasters were reported, and this is taken from the ADINET website, the link is there. So in that area in eastern Indonesia where we're predicting from 3 weeks before an increased chance, there were actually several floods reported and affected more than 22,000 people. There's also flooding reported in northern Sulawesi, although in this case, fewer people were affected. Finally, the biggest number of people affected was over Thailand, Laos, PDR, and Vietnam, where the remnants of Tropical Storm Sinalako affected more than 100,000 people. This was not really predicted very well at the subseasonal timescale. And this is something that we find that tropical cyclone activity or rainfall from tropical cyclone activity is not well predicted by the subseasonal models, at least without further calibration or more specific targeted approach. So overall for this case study, which was quite representative for our experiences, that we can see that in some instances there's good predictive skill. In this case, they were tied to MJO activity, for those who are familiar with MJO is, but unfortunately there were some smaller events that were missed, as well as the larger event associated with tropical cyclone activity. This case study was actually part of a pilot project with the partners ASMC, the ASEAN Coordinating Center for Humanitarian Assistance on Disaster Management, RIMES, as well as UNSCAP. And actually between February 2020 and 2022, we issued 52 outlooks, subseasonal outlooks. And then looking at this 3 weeks, so 3 weeks before what we've showed here, we did have quite a few misses, like in this case study where we're talking about what happened in Sumatra and also over parts of mainland Southeast Asia. These would tend to be either localized events. Of course, not all floods are triggered or solely from rainfall, or it could be something associated with a phenomena that's more challenging to predict, such as the tropical cyclone activity. However, we found that the number of false alarms was quite low. So this is when we're saying that we indicated an increased chance for extreme rainfall, and then there were no disasters ended up happening in that region. And actually, so there were, throughout those 2 years, there were 50 regions that were identified 3 weeks before as having increased chance of extreme rainfall. And only twice did there not end up being a disaster in that region. And this low false alarm does open the avenue for actions such as forecast-based financing. Okay, so I didn't have much time, so that was a quick window into unlocking S2S for disaster risk reduction. But there's 2 points I would like to sort of make now, and then perhaps we can discuss more during the question section later. The first, of course, is that the scale of the subseasonal timescale does vary. And this is even true in a region such as Southeast Asia with relatively high skill. So it's likely that there will always be certain types of events that are predicted better than others. And of course, there are techniques that we'll hear from other speakers as well that we can do to improve the skill, use different model combinations, different sort of calibration or machine learning techniques. But in many cases, it'll end up being a trade-off between more sort of what we call hits, like raising awareness, and then also balancing that with increased number of false alarms. So you have to sort of do this trade-off. And this ties into my second point, is that it's really important to develop products with the people that are going to use them. Make a forecast truly useful, there needs to be actions that can be taken based on this information. So the products both have to have skill, but they also have to be applied. So in the case that we were talking about, that we were showing when there was relatively or quite low number of false alarms, this makes it a good candidate for forecast-based financing, but perhaps that's not the goal, you want to do some other actions. And I also just finally want to say, even if you don't necessarily have good skill for extremes, but you want to help with this disaster management, it can also be useful to look at the information for planning and for planning the recovery afterwards. So after you have a disaster, it can be useful to know, is it going to be more likely to be wetter or drier in the coming weeks after the disaster as well. So hopefully this short presentation has convinced you that subseasonal forecasts should be considered as another string in one's bow, including other things like weather forecast, to help people better prepare for disasters. Thank you. So I'll finish there.
Great, thanks, Thea. I know your presentation certainly generates some questions in my mind. I'm hoping when we get into the Q&A session, there'll be others from the audience as well. So up next is John Davis. John is the Chief Meteorologist at Everstream Analytics, where he leads the Weather and Climate Division for Energy, Agriculture, and Supply Chain Logistics. John is based in Barcelona, and just so everyone knows, it is 2 a.m. in the morning where John is right now. So he definitely got the worst curtain call, if you will. So he's based in Barcelona and brings over 35 years of experience and is widely considered one of the foremost experts on the impact of weather and climate on global commodities and business. After graduating from the University of Wisconsin in Madison with a degree in meteorology, he spent 18 years on Wall Street in the commodity divisions within Citigroup as chief meteorologist and 11 years at Chesapeake Energy as chief meteorologist. In 2015, John was given the prestigious award for outstanding contribution to the advancement of applied meteorology by the American Meteorological Society. In 2017, John was awarded the Kenneth C. Spengler Award for outstanding vision to advance the role of meteorology in the new energy economy and the outstanding leadership of the American Meteorological Society Energy Committee and its conference. John, we're all looking forward to your presentation. Please take it away.
Right, Jan, thank you so much. And here in Barcelona, we're just now beginning to eat dinner. So this is kind of a normal night here in Barcelona. So let me share my screen, and thank you so much for having me. It's great to be here. Yeah, so my take on subseasonal forecasting is going to be a little bit different. And it's really going to be from a standpoint of some of it's going to be communication to the end user. And how do we take very complex scientific data and make that in a case to the user where they can make decisions on that, especially from a subseasonal forecasting standpoint here coming up. So it's one of the things I'll kind of talk about overall. Just kind of a quick background as to, what do we do, as a company in my space? Well, what we do is we provide predictive and prescriptive insights for the world's most complex supply chains. Part of that is weather and climate related. So anything that disrupts the supply chains, and the supply chain is all end to end. So it starts with agriculture, it starts with energy, goes through the entire process of making things, and then transporting those things to the consumer or to places overall. So it really is an end-to-end standpoint. So weather is a part of how we look at risk overall. There's lots of other things here that are, risk from a standpoint of supply chain logistics and within the supply chain. And all of us know a lot about those that have come up in a very big way, over the last couple of years. But from a weather and climate perspective, how do we take the information and take that and look at risk? So one of the ways we do that, and we'll first of all talk about kind of the short term, is making it easy for the user to be able to look at risk. So this is just an image of our platform that we have. These are the major global ports across Asia, one of the cores of our business, along with Europe and North America. But we look at risk from a shorter term standpoint and all the things that cause risk in all the global port operations out there. And then we look at that and then score on that risk to kind of use the basic stoplight situation. Green, there's no reason to worry. There's no issues at the port. Yellow, moderate risk, something to watch. Red, there's high risk. You have to take action to change your operations here overall. So this is how we think about risk overall. This is just an example of the major port operations. And then that is the short term, which we're not talking about here today. So taking things up into a bit more complex standpoint, how do we use information from this subseasonal overall, something that's very important, to our client base, and begin to take some of these issues and talk about probabilities and make them in a format to be able for the user to make decisions that are smart on that overall information. So, this is just an example that we're going to use in taking some of the complex things we look at, obviously ENSO and our ongoing La Nina event, which has had huge ramifications out there. And then subseasonally, looking at, MGO cycles and how does that go within the subseasonal time frame in a base state of La Nina, and then getting into IOD configurations here overall. So that information, how is that translated, to, the end user so they can make smart decisions and limit their risk or mitigate their risk in a subseasonal time frame? I thought the best way to do that would be use an example of some of the research that we put together, and what does the end user want to know? They don't really care, what MGO phase that we're in. They don't care if it's a positive, negative IOD. They don't really care what ENSO is doing. What they care about is the things that they're looking at, procurement and logistics in their specific company. So to do this, this is something that's happened. One of our clients here in Southeast Asia, over the past couple of months, and they're a client that brings in a great deal of agricultural products overall here, and they can ship them in. And so their concern is availability of agricultural products and being able to bring that into areas of Southeast Asia. They can go anywhere in the world to get their products, but they have to have their products overall. So when we put all those subseasonal variables together, and here we kind of look at water resources, and this is kind of our current water resource tracker. And in looking at the subseasonal issues and the wetness that in general we've seen across much of Southeast Asia, down through most of Australia, and that's been ongoing for the last couple of years overall, versus the dryness that we've seen across South America, kind of a textbook or classic La Nina situation overall. And again, this has been in place, meaning more wetness issues across Southeast Asia, more dryness or drought issues or lack of water resources across South America. So with La Nina continuing from all expectations through year's end and probably into the early portion of next year, how does this influence the decision-making process? If you're sitting, in Southeast Asia and you're interested in global agriculture, in sourcing, the agriculture that you need to whatever you're going to make or produce or sell in the business that you have. So again, the issue, the risk is wetness in Southeast Asia. That has been the case lately. That will continue to be the case as we go through the end of this year. From an agricultural standpoint, that's good and bad. So the good is that you don't typically tend to have serious drought across Southeast Asia. So crop production tends to be relatively good, but you tend to have quality problems, too much moisture, increase in mold counts, lack of harvest activity or delays in harvest activity. So you tend to have problems here in the logistics of agriculture, bringing it into your site. Versus, let's say, South America, the big producing areas of Brazil, Argentina, Uruguay, and Paraguay, where dryness and drought has been the problem lately. So that impacts production here overall. And that is the area where if you're sourcing, and whether you're interested in getting crops from an area that's going to have drought issues like South America, the quality likely is fine, but the drought issues will reduce production overall. So as companies begin to think about, subseasonally, the next couple of months through the end of the year, bringing product in, where do you source from? Where are you going to have quality degradation? Where are you going to have more harvest delays here, movement of the crop, supply chain disruptions here overall, and where are those issues going to occur across different areas? So this is an example as to, that help them to source where they're getting their agricultural products, fruits, vegetables, other items here out there, basis on subseasonal research and looking at areas that have wetness issues, Southeast Asia, dryness issues, South America, and this will likely continue here through the end of the year across the area. So the risk remains the same overall across these locales. So that's just a way of, communicating to the end user, in this case, the client, as to the risk here going forward in using, very complex subseasonal, issues to make decision-making easier for the end user, in this case, an agricultural buyer here, you know, bringing product in and out of Southeast Asia overall. And with that, I'll turn it back over to Jan.
Great, thanks, John. It's very nice that you were able to do your whole discussion without showing a single probability map. So next and last but not least is Dr. Mary Beth Arcodia. Mary Beth is a postdoctoral fellow in the Department of Atmospheric Science at Colorado State University. She is currently researching sources of predictability within the Earth's climate system on the subseasonal to decadal timescales using explainable machine learning. Her work includes utilizing climate models and observational data to understand large-scale connections to identify and improve forecasts of opportunity. She received her PhD in atmospheric science from the University of Miami Rosenstiel School in 2021. Mary Beth, please educate us on a very hot topic in all forms of weather forecasting and long-range forecasting, the role of artificial intelligence in climate science.
Thank you. So the other speakers have really paved the way here for me. Okay, so I'm going, as Jan mentioned, I'm going to be talking about leveraging artificial intelligence to understand the climate system. And so, as been mentioned before, the subseasonal timescale is often considered a desert of predictability. And so it falls in this 2-week to 2-month timescale, which falls in between our weather and climate timescales. But the forecast skill during this time period is exceptionally low. However, it's important because it's known as a bridge between weather and climate, and consequential phenomena fall on this timescale, like we've been discussing, such as flooding and drought events, heat waves, and other climate phenomenon. And so, because of this desert of predictability, we need to rely on predictable states of the climate system to improve these subseasonal forecasts. And these predictable states are known as forecasts of opportunity. And so for these subseasonal forecasts, and to make these forecasts of opportunity, we really need to have a knowledge of the full global system, especially for regions in Asia, Southeast Asia, as has been mentioned, and North America. We often rely on the state of the tropics. And as John referred to, we look at the ENSO state, the state of MJO. And here we can see as these storm systems are moving across. Here we're looking at the Madden-Julian oscillation, or the MJO. This interferes with our jet stream and can affect rainfall that we see in the United States. And so where does artificial intelligence come into this? So here we have what's known as an artificial neural network. And what we give this network, or this machine learning model, an input image, this 7. We feed it through this model and it makes a prediction. And here it makes a correct prediction, a 7. And so we can use this artificial neural network setup to make predictions about the climate system based on user-specified input data. And so an additional aspect of this artificial neural network that we can use is that it also outputs a confidence in its prediction. So see here we have our 5, 6, and 7, and then we can use a softmax function to then convert these outputs into a probability. And here we see that the network has a 67% confidence that the image is in fact a 7, and so then it chooses that output. And so by using this neural network, we can actually quantify the confidence in the probability of a predicted output. So now let's put this into context of the climate system. So one technique that we can use here is to use the state of the climate system. Here we're looking at daily precipitation in the tropics. We feed it through an artificial neural network, and then we look at an output, which is the rainfall anomaly along the west coast of North America on the subseasonal timescale, or weeks 3 to 4 later. And so our goal here is to predict the sign of the subseasonal precipitation anomaly along the North American West Coast using the state of the tropics. And so our output is either a positive or a negative precipitation anomaly. And so this directly translates into forecasts of opportunity through that ability to quantify our confidence in our output. So we can categorize our outputs over a certain time series into our most confident. And then if we isolate just those most confident, say here are 20% most confident forecasts or predictions, we see here that over time, as our predictions get more confident, they also get more accurate. And so this is exactly where we see these forecasts of opportunity. And so now we isolate just those forecasts that were the most confident, and that's what we see here in the black line, and we separate these from our least confident, or these predictions here are least confident, least accurate predictions. And so what we see here, and if we look over a certain 100-year time period, let's say, we can see that our least confident, least accurate predictions really hover around 50%. And this makes sense because we only have two outputs, either more rainfall or less rainfall than normal. So the network doesn't really have much confidence or accuracy in its predictions. But when we isolate those confident forecasts, we see that we actually have these big changes in accuracy over time. Additionally, we see that there's certain 5 to 10 to 20-year time periods where our accuracy is actually quite high, especially compared to the average. And so what we see here is that we have these certain 5 to 10-year time periods that have higher predictive skill and higher forecast confidence. And so we can leverage artificial intelligence, specifically these machine learning techniques, such as artificial neural networks, to actually quantify our predictive skill and confidence. We have found that our predictability of subseasonal precipitation can actually vary on these low frequency timescales. So what that means is that we can have certain decades where we actually have higher accuracy in those subseasonal, those week 3 to 4 forecasts. And then lastly, we can use these machine learning techniques to really open up our black box to understand or explain what the machine learning model is learning, to identify these forecasts of opportunity based on both confidence and accuracy of the network. Thank you.
Great. Thanks, Mary Beth. So that concludes the presentation component of today's webinar. And now we're going to move over to the second part, where we're going to have a panel discussion, hopefully supported by questions that are coming from our audience. I guess what I would like to do is I'm going to start with a very basic question. I'm not going to direct it to anyone in particular, just someone raise your hand if you want to answer it. But in today's presentations, we were talking a lot about probability forecasts, and so a deterministic forecast, right, is let's say is a 3-day forecast for the temperature or the wind speed for your particular location, whereas a probability forecast is the probability of a certain level or a certain condition being reached or exceeded or something like that. So the very basic question is, why is it necessary that long-range forecasts or subseasonal forecasts are probabilistic?
I can answer.
Go for it, Mary Beth.
So one is that we are just simply past our predictability barrier of being able to make a deterministic forecast, and that's that weather timescale. So beyond about 15 days, we aren't able to make a prediction that, say, the temperature tomorrow will be 30 degrees. And that's just because we've lost the amount of information from when our forecast models were run. The second reason is because from a user standpoint, a probabilistic forecast is has a lot more information to it. And so if you say that it's going to be rainier than normal in, say, 3 to 4 weeks, that means that there's some sort of preparations that you need to do, perhaps lowering water levels, getting infrastructure ready for flooding. But if you say it's going to rain 10 centimeters in 3 weeks, the basic non-standard weather person is not going to understand how that means relative to normal. And so it's from both a capability standpoint and from an understandability standpoint.
Great. John, I'm curious, are you communicating probabilistic information to your customers, or are they looking for, quote unquote, the answer?
No, probabilities. And, Mary Beth answered that perfectly, is that we do not have the scientific skill to do deterministic in a subseasonal time frame. We do have the skill to do probabilistic forecasting. And as long as you have a good relationship with your clients and you work with them year after year, they can deal with that just fine at any level out there, as long as you present that in the right way. But it's by far the best way to do it, the best way to present it. And all clients deal with it very, very well. And that's what they want. And I think that they understand that the skill is not there. Maybe in 20 years, the skill will be there to some extent, but it's not there now, and they get that. But that's what they want, is, the best bet into what the decisions that they're making.
Great. Thea, you mentioned the probabilistic forecast for Southeast Asia. Do you find that end users struggle to comprehend or struggle to use the probabilistic information, or does it tend to be pretty straightforward once they get a handle on it?
It really depends on the user from our experience. If the user comes from using climate seasonal information, it tends to be easier because that has always been, for talking about the probabilistic sense. Similarly, we found that actually with our work with the disaster agencies, it actually, because they're used to thinking of risk, and that's, the probability of hazard and the impact. So they're fine with it. But other users that come from the weather forecast, which, as you said, typically tends to be more deterministic, these do struggle. They do struggle. They want to know. They want to know what will happen. And of course they want to know what's going to happen, but we can't say that, right? And as Mary Beth rightly pointed out, and John, that there's so much more if you think about it in a probabilistic sense. You're getting more information from that.
Yeah. Nachiketa, in the experience you had for the monsoon forecasting in India, was the information as it was communicated understood in the first pass, or did it take several rounds of back and forth before the product was at a point where it could be consumed and decisions made from it?
Yeah, sure. I'll answer your thing, but before that, I want to just give my feedback on probabilistic forecast.
Sure.
It's important for the climate. So for me, like, two things is very important. One is, like, in the probabilistic forecast, you also convey the uncertainty of the forecast. Like in a deterministic forecast, is like there will be 30 millimeter of rainfall. So there is no uncertainty, rather it's a 100% confidence forecast. But in a probability, you always give a different kind of probability for different kind of thresholds. Like this is the chance of 75% of having heavy rainfall, but still it's like 25% of chance is not heavy rainfall. So it's always give the users to take the risk management, and which I actually experienced when I'm communicating the probability to the policymakers in the seasonal forecasting sense, and also the subseasonal forecasting sense to the farmer. And they kind of make this multi-crop decision based on this probability. Like, okay, so rainfall is important for this particular crop, but there is still 25% chance that rainfall will be not that way. So they go for the multi-crop system. I think that's the power of probability and the dissemination of probability, as John and Mary Beth and Thea mentioned, that if the customer is actually understand what does it mean, is actually really helpful. And here is my own experience. Like when we always kind of underestimate the customer's understanding of probability. Here's an example. I talk with this Department of Agriculture Extension, some officials, and they are kind of so much understand the deterministic forecast in the weather scale, as Thea mentioned, that doesn't understand how to disseminate that probability. But when I talk with the farmer, they understand very easily because farmers start with a chance. Like, what is the chance of rainfall today? So they understand the ground, like the grassroots level user understand the probability much easier way than the medium, like media person. So that's my understanding. So the probability focus has a lot of more potentiality than the deterministic focus, especially on that scale, whether the scale is so uncertain. So yeah, that's my experience. Thank you.
Yeah. I wonder, maybe John can probably relate to this. So I've worked with lots of meteorologists on energy trading desks and then traders on energy trading desks. And I will say, because a trader's job is many times absolutely dependent on understanding the forecast information, it's incredible what they can learn. And they have like a PhD in meteorology from the School of Hard Knocks because they've been forced to learn the information. Both Thea, I think it was Thea. No, it was Nachiketa and Mary Beth showed a diagram of the gulf of predictability between weather forecasting and climate forecasting. And so there, in particular, there was a one diagram showed the subseasonal forecasting being particularly low. However, Mary Beth talked about forecasts of opportunity and discussed that when there are high probability forecasts, those forecasts are more likely to be correct. So one question for the panel then is subseasonal forecasting skill being mischaracterized as being low skill? Meaning, are people assuming that it's generally low skill, when in fact the research has shown that there are times when, you know, a week 3 forecast for temperature can be correct 80% of the time in an extremely high probability forecast. So I guess what I'm asking is, should that diagram maybe be redone to somehow show that there are times when subseasonal forecasts are actually highly skillful and very useful? Anyone, go for it.
What?
No.
Just go, Thea, go.
I was going to say, actually, yeah, we have already done the diagram for Southeast Asia. Because we are, like, if you look at global maps of skill, we are in a region with high skill. But I think, yeah, so it really depends on where you take. I mean, you do a global average, it yeah, can move those regions that are higher skill. But I do think the point is that when we talk about these like windows of opportunity that Nachi said, it's not that it's going to be even high skill all the time. So I mean, I think what is the point that we're trying to get across here? I think we don't want to give the impression that we can do it deterministically as good as a weather forecast. We can predict everything. We have to be realistic that there are these windows of opportunity where it is better. And then there's others, I don't know, doors of despair, I don't know, where you can't predict. So maybe it's a question of showing that and then just re-emphasizing that, hey, there are opportunities where we can do it. So an additional diagram on top of that one, maybe.
Right. John, did you want to say something?
Yeah, my quick take on that is I think that graph is rapidly changing, and it's changing every year from this point on. A great example of that, look at this summer. The predictability of subseasonal with the drought in Europe, with the heat wave across the plains in the Western US, that was very well forecasted weeks out. And I think we're seeing more and more of that. Some of the drought conditions across central China and the implications on hydro there, forecasted very well weeks in advance. So we're getting much, much better at subseasonal. I think that graph is changing pretty rapidly right now, but that is the area where it can change. But I think we're seeing it happen in front of our eyes.
Yeah, John, I have a fairly straightforward case study burned in my brain where last January, temperatures in Argentina reached 105 degrees in some of the key agricultural growing regions. And so a properly calibrated subseasonal forecast had above normal temperature signals 6 weeks in advance. And then as you went closer to the real-time forecast, the probabilities just increased through time. And so it was, you know, the models were showing high probabilities of warmer than normal 3 weeks in advance. And like similar to what Theo was showing, like if you looked at the maps, it's quite remarkable how accurate that they were in that case. A question, a question from the audience for Thea. It reads, your presentation covered flood-related disasters, focusing on conditions over a week lead time. Is it possible to apply subseasonal forecasts for slow onset disasters such as drought?
Yes. I think also John covered this a little bit in his presentation, but it can be useful as well. So in our pilot project that we were looking at, it was actually also, as other people have said, it was during when we had a lot of La Nina events and negative IOD events, which doesn't tend to be didn't lead to a lot of droughts. But in other previous case studies, we've shown that you can look at, especially during the onset and termination phase, it can give you some more finer details in between that sort of seasonal time scale, which we more traditionally look for droughts, and the weather forecast about when these drought conditions might start to be alleviated or onset as well.
Great. And a question came in for Mary Beth. Mary Beth, how does machine learning answer questions about the climate system that other older or more classic methods do not?
So machine learning has been around for a really long time and has only recently been applied. Actually, Nachiketa showed an example from a number of years ago, but it's really taken off lately because of our ability to open the black box of that neural network. So if you remember that image I showed of the 7 passing through, it can look really complicated, but we have techniques to be able to understand what the machine learning model actually learned to make its prediction. And so machine learning is not a magic answer. It's not the magic key, but it is an additional tool in the toolbox. And so by looking into what the network learned to make its prediction, we can actually learn some new science that we didn't know before. So for example, we can identify some additional sources of predictability. We're able to more easily quantify our predictability and isolate our confident forecast, as I showed in my presentation. Nachiketa, I don't know if you want to answer this as well, as far as some additional examples. So machine learning is used in addition to classical examples to really help us learn new science.
Sure, Maribeth, I just want to chime in one thing, like when you see the older or classical methods, all the methods based on kind of a linear system, like for example, linear correlation between ENSO and rainfall, or linear correlation between North Atlantic oscillation and temperature. So although as a student of statistics, everything fall into the machine learning, it's only like it sort of depend whether it's supervised learning or unsupervised learning. So most of the method is kind of based on supervised learning, where you put the assumption, whether it's a linear correlation, whether it's a normal distribution. But using the newest method like Maribeth and we are working, where we don't start with any assumption. We're looking the nonlinearity of the system. And from the data-driven method, we understand, which we don't understand before we start the network. So I think that's kind of the opportunity we should use the explainable AI such a way we get some new information from the model itself, rather putting information. I think that's the key of the success of the machine learning. Thank you.
So my take on some of the questions that can be answered about the climate system, to draw on Nachiketa's comments, is that the machine learning or artificial intelligence, depending on your vocabulary, it provides an opportunity to extract some nonlinear relationships. And through those nonlinear relationships, we might find basically we might discover new science about the climate system that we didn't know using only linear methods. However, like when I read about artificial intelligence, I'm reading about things like, Google tracking billions and billions of data points, and that they're using artificial intelligence to improve our search query results and things like that. But they've got billions and billions of data points to do that. In our climate system, we have 100 years, 120 years of data maximum. So let's just call it 1,200 months of data. Where is the balance between finding the nonlinear relationships and the amount of data available to find them? Because there has to be a limit somewhere.
John, can I start with? Then
Yeah, go ahead.
I mean, yeah. So that's something I really want to, I'm really happy that you mentioned this thing. You said like 120 years. In fact, in the subseasonal scale, we are just dealing with 20 years or 30 years data.
Right.
Much lesser than that.
And can just explain why that is.
Yeah, the reason because like to improve our system from a weather prediction or dynamical model, we need to add some information for the observation. In other word, like each of the climate model before they go for the operation, they also run the past forecast, or we call reforecast or hindcast, to show the confidence. And whenever we do calibration of any kind of real-time forecast, we always use those data set to match whether they, how much they like associate with the past climate. Like for example, ECMWF, the best model, we always go to the ECMWF last 20 years forecast and see what is the 20 years of the observation and how close they are. If it is not, we try to use kind of machine learning or statistics to remove this bias and that correction factor to real-time forecast. That's what, and it's very expensive to run those climate forecasts for 120 years or 240 years. It's better to run 30 years. And also the climate has changed. So we have to focus on that last climate. So coming back to your main question, like it's always trade-off between like the data-driven or data-hungry method to implement on those kind of data, those kind of climate forecast. So that's what I think it's very important to understand the domain knowledge of artificial intelligence. Instead of using a random package from the Python and start deep learning, we have to understand which method can work for which problem. For example, if the problem is improve the calibration within 20 years, you just go with the single feed forward neural network instead of very deep learning in different layers kind of things. I think like it's a choice of the scientist how you use your tools. Rather, for example, there's also other importance of machine learning where people use it to solve the differential equation within the climate models. And there you can use a lot of different deep learning because you have 6-hourly data for 20 years. So I think that's kind of trade-off. Like again, machine learning is not a magical box. Rather, as Maribeth said, it's always there. It's an additional tool, and you have to understand which screwdriver works for which nails, right? I think that's the way it should work. For the Google example, what you do, like that's kind of another example where they kind of use more and more data to accurate their forecast. But we are talking about the accuracy, which is if it is more than 50%, we are happy because of the complexity of the system. So I think that's the whole point.
Other panelists, do you want to add anything to that?
Another aspect that really catapulted us using machine learning is our ability to utilize climate models. And so that's another way that we can get around this lack of observational data is we have these large ensembles, so hundreds of climate models that run these really long simulations of the climate system. And so we're able to train those data hungry models and go back in and learn. So when ECMWF makes a prediction, and it's wrong, we don't necessarily know why it was wrong. But in a machine learning model, we can go back and figure out why it was wrong or why it was right. And so by utilizing climate models, we can then help address that lack of observational data issue. And also machine learning is really good because there is on the other side so much climate data. Sometimes it's just too computationally expensive to handle that amount of data. And a lot of machine learning methods just help us to do things faster.
So Maribeth, just to let me tell you what I heard you say, because the climate model is a representation of our atmosphere. Granted, it has some assumptions, but we're trying to represent the physics of the atmosphere. That we can run that model over very long time periods, and then the physics, and then we can use machine learning to understand the physics of that climate model, but then apply that learning to the real world to try to make predictions. Is that right?
Exactly. The climate models are our best representations of the climate system, and we have hundreds of them. And so we're able, while we only have one Earth that we're living on, to be able to use the observational data that we have, we're able to utilize hundreds of climate models to then feed these data hungry models, so it has more data to learn from.
Great. So a question from the audience: what variables is a neural network usually trained on for subseasonal predictions, other than precipitation, which we've talked about in the presentations?
To get at Nachiketa's point a little bit, that totally depends on the question that you're asking and the tools that you have available, the computational resources, as well as the region that you're looking at. So if you wanted, you could feed in all of the climate variables that we have. It would take a really long time and have a lot of nonlinear complexities to it. Or you could just use one variable, like the example I showed, from one region. And so so it depends on the type of forecast that you're trying to look at, but you're able to use even the same variable for the same location if you wanted to make that prediction.
Great.
I may add a little bit of Jan on that.
Yeah,
Like,
go ahead.
yeah, as maybe say, like, what is the end product? For example, you're looking for heat wave. So, or we're looking for some kind of wind. So it's the input variable is important. And now there's a two different kind of machine learning. One is like from one variable to same variable, we call autocorrelation based. Like, if you want to know what is the wind for next 3 weeks based on the last, couple of weeks, you can just train the neural network on that. Other model is like that we call the multivariate model, like how the sea surface temperature or outgoing long wave radiation impact on wind, and you want to use that relationship in the network. So you can use a lot of other variables to train the network to find the end product.
Great. We're going to go for a general question here that hopefully everyone can contribute. And the question is, where do you see growth areas for the use of subseasonal forecasting by both the private sector or the public sectors? So in other words, where is subseasonal forecasting going, and where will it be applied, do you think, where it hasn't been applied already? Let's see. Thea, I'm looking at you.
A very general, obvious answer is it's going to
Yes.
go wherever you can take decisions or make actions on that, right? Using the probabilistic information. I mean, I do hope that it will go into, where our focus is that sort of disaster management. But I do think there's obviously a lot we heard, both Nachi and also John were talking about in the agricultural sector, food security, this sort of thing. I think that's also a really key, important area where it's going to go. But yeah, I think it's anywhere where you can make decisions. I think I don't have the answer to this question, but something that I do think about is how useful it is for the general public. Like, should we be having subseasonal forecasts on the websites? Should all Met services have this? And I don't know the answer to this question because it is, as we've also heard today, quite complex information, right? It's not deterministic, but at the same time, we also hear that from our experience, and we heard from other panelists, that when people are presented with, they get used to the information, they get used to dealing with eventually, they will hopefully learn to use it over time if they say it repeatedly. So yeah, so to go back, anywhere where you can make decisions on that time scale based on the climate information, yes, but I'm not so sure about opening it for the general public and that sort of thing.
Well, I will say my experience, again, it's back to understanding probabilities. A family member who will remain unnamed, might look at a precip forecast for the afternoon and it says 60% probability of precip. And that person says, oh, it's not going to rain today. And I'm like, what do you mean? It's 60%. So I'm not sure. I'm not sure it makes sense to distribute that type of forecast, say via a mobile app, except to specialized users. Nachiketa, where do you think it's going?
Yeah, I want to add one thing, always this is in my mind. So the subseasonal forecast cannot be seen as independent forecast timescale. It should be within this weather forecast, subseason and season. Mostly I can say weather forecast and subseasonal go together. And that's what I really like. 3 years back, I worked with the Red Cross Climate Center, and they use a point called ready, set, go. So the ready is something like in the long range forecast or seasonal forecast, where you get some kind of signal in the season. Then the set is this subseasonal forecast, where you can actually look at the forecast map and try to make your contingency plan, and the go is a weather forecast. So I feel like set go should go together. I have experience with working on India meteorological, Bangladesh meteorological, Ethiopian meteorological, and mostly we are looking at the tropical cyclone, and where we actually start looking this 3 weeks, 2 weeks, 1 week, different scale, looking at kind of, any system happen, and kind of combine this weather forecast and subseasonal forecast together, because in subseasonal forecast, we are not expecting this scale in magnitude, rather getting a signal. And then the weather forecast, you get this, you're expecting the scale of magnitude, like where the track goes or what will be the category of the tropical cyclone. I think the growth of subseasonal forecast should go with the weather forecast along with.
Okay, very good. John?
Yeah, just kind of expanding from Tia's comments as to, I think the industries that have the most exposure to weather/climate risk, that is kind of the sweet spot going forward. Obviously, agriculture is huge, energy, supply chain logistics as well, and kind of improving that overall forecastability with all those. And again, being able for countries, companies to mitigate risk with better subseasonal forecasting overall. But I look at that from an industry perspective, and the industries that have the highest exposure to weather climate risk, especially in the subseasonal.
Great. Mary Beth, your thoughts?
Yeah, just to add to all three of those comments, my hope would be that this information also gets used a lot more by local governments and decision makers. So also, as Thea mentioned, so that local government officials who are actually making decisions about how to prepare are fully equipped on how to read these forecasts. Like we said, it's important to understand this information to use it properly. And so, that's a really important that's a really important sector, is the local government and decision makers. And then from a research standpoint, I see this from the machine learning standpoint, it also using a physics constraint. And so as Nachiketa mentioned in his presentation, you have this statistical model and this dynamical model to make the subseasonal forecasts. And so in a similar way, we have these machine learning data-driven models that are also constrained by the physical world. And so we're really mixing these two tools that we have to advance subseasonal forecasting.
Great. Yeah. I'll say I see it as to combine a couple of the thoughts that we've talked about in terms of what is possible to forecast. I mean, anything is possible to forecast in terms of a meteorological parameter. It's just a question of whether we have the data to do it, and then what we can extract from the model to try to forecast that. So in terms of where the application or the use of subseasonal forecasts is going, I see it as, we have this ever expanding set of observational data in terms of weather and climate conditions. We have an unbelievably expanding set of sort of business parameters and health parameters and risk parameters. There's always new data sets coming available, and the degree to which we can find relationships between weather and climate and those business and those health, let's say, or non-business related parameters, and then we can forecast the variable that is impacting that. The potential applications for subseasonal forecasting to provide early warnings or to create opportunities before people that are using only weather forecasts. I think the opportunity is quite substantial, and I'm sure that it's going to happen. It's the natural progression of the application of information in our society. And just as an example, right, Nachiketa mentioned the Python package that he is instrumental in developing to enable the application of subseasonal forecasts. 5 years ago, nothing like that existed. 5 years ago, there was only 126 references to subseasonal forecasting in the AMS publications. And now Nachiketa is releasing a Python package so everyone can do it on their MacBook if they want to. And so I think we're still very early on in the science and the applications of subseasonal forecasting. And both the private sector and the public sector are going to benefit substantially from the science.
Yeah, and I just want to add one thing. Like, that is what we really need to revise this plot, because the plot is, I think, like before the S2S project by WMO, we created that subjective plot. Now we have like the strong climate models, machine learning. So there is a need to revise this plot.
Yeah, we should start a Twitter hashtag subseasonal. Hashtag subseasonal is skillful when we start tweeting subseasonal information. John, a question for you. In supply chain logistics, what is the biggest need or item of concern?
Good question. Biggest item of concern right now, I think, is extreme weather events. Those events, which are at the tails of the distribution. As we all know, the supply chain is kind of teetering over the last 3 or 4 years, and any little disruption within the supply chain has ramifications on a global scale. And one of the items that can cause big issues is extreme weather events. The obvious ones, typhoons and hurricanes, things like that. But other items like strong wind events here in the North Pacific and the impact here on container ships and the routes that ships take across the North Pacific, heat, in Europe this summer, and infrastructure is just simply not ready for the kind of heat that we have. And so many of the, I think, companies, this is maybe a little bit more so 3, 4, or 5 years ago, but so many of the companies that we work with, they just kind of think back to history and don't think in the way of extremes like what we're having lately. And they tend to be really hurt by that, actually. And so I think extremes is the item that is the biggest impact from a supply chain standpoint. And because we're in such, precipitous times here, these extremes that occur cause huge ramifications and reverberate around the world. I would say this is at the need. I think it's what we're talking about. Better forecasting short term, better forecasting subseasonal. I think climate, as well, but subseasonal and short term, the better the forecasting, the more you can mitigate risk here over time. And even small improvements in the forecast can mean a lot from a standpoint of, impacts down the line and how big those impacts become and how they reverberate around the world.
Great. So I think it's interesting that you mentioned extremes, because Thea talked about forecasting precipitation extremes and really highlighted some pretty remarkable statistics in terms of the ability to forecast the events in terms of the hit rate and the miss rate.
Right.
And so I guess I want to say we're there, but we've shown skill, and there's obviously much more to go as the research community wraps in many of the ideas that we're talking about today.
Yep.
Great. Mary Beth, you mentioned gaps in the observational data and the potential role of machine learning. How significant are the gaps in observational data, especially when it comes to less well-off countries who are probably hardest hit by the impacts of extreme weather?
Yeah, that's a great question and highlights a really big issue, which is the lack of observational data, especially as the more vulnerable communities. And so the more observations that we have and the better that they are, the better the forecasts are, because we have a better idea of what that initialized state is. So we do use some techniques to try to fill in the gaps. One is data assimilation. And so we're able to take the observations that we do have and then basically fill in those gaps. But the more observations that we have and the better that they are, the less that we have to fill in the gaps and the more that we get on the ground information. We also have satellites, which do help a bit with that global coverage. But that is certainly an issue, is a lack of that observational data, especially in the poorest regions of the globe. Another issue in those regions is disseminating that information. So if there's a warning that a flooding event that's very well predicted, but it doesn't get out to the community, it's not as helpful as a forecast. So whoever asked that question, you hit on a big issue in our field that is being addressed.
Great. Any other comments? No? Okay.
Maybe I was just going to add on to
Yeah,
that.
go
Yeah,
ahead.
so like observational data is really key for everything. Like I'm not sure if she was talking. The question was asking about machine learning, but yeah, even for our subseasonal models, right? Like, and there it becomes and any of our weather forecasts, seasonal models, everything. But it's a seasonal time scale because as I cannot remember who put it in their presentation, but they highlighted that you have to include, it's like the whole globe, right? Weather systems are traveling around the globe. So it's not just the observations in the ocean. And that is also a place where not many people are living, but it's also key to get observations, not just from the countries, but our whole climate system. We need to get good observations.
Yeah. Well, in fact, we wouldn't, as you said, like observations are really the lifeblood of the forecast process, because it's what we're trying to predict and it's how we improve the models and how we verify the forecast. We can run climate models all we want, but if we're not measuring it against or comparing it against something, there's not much benefit there. So each of you discussed potential applications of subseasonal forecasts. One question from the audience then is, how involved are stakeholders in creating graphics or other tools to help visualize the data that you're creating and to help understand the impacts of the subseasonal forecast? I guess, Thea, you are filling the screen and you have maybe some of the most experience with presenting the information. How involved are stakeholders in your process?
Definitely very important. Typically, we will develop something and show them and see how they understand it. And we've had suggestions about how to better understand it, how to understand probabilities. So some people, for one example, we have the sort of the pie chart. And I know sometimes this is not the best tool to use, because a pie chart, you have the circle and then you fill, because it adds up to 100%, right? You should have, like, your probability should add up to 100%. So you show how much each sort of category is going, and it sort of works better. It doesn't work really well for extremes, but if you're looking at something not so extreme, users have found that they interpret it better. But yeah, it's been really interesting to see how users incorporate the information, like how they understand the information, and that's really key. But I would say from experience as well, understanding skill maps, hence I didn't show any in my presentation, is very hard for users to understand. Yeah.
Nachiketa, what's the role of stakeholders in your experience?
I think that's the biggest, actually. Like, one part is science, to understand the science. The other part is like understand the demands. And the biggest thing, what I say, the biggest is to convince the users that whatever you want, we can provide. Like, I remember working with the agriculture sector in Bangladesh, and I was in a meeting and somebody asked, like, I need information for next 6 months, every day, when this wind will be happen, because that's so important for my rice. And he was like, you guys are not working at all, because we're actually expecting that kind of information for the meteorology department. And that's what like kind of intervene, like, you have to understand the limitation. I can predict anything you want. I can predict what will be the rain on your roof, but how confident it is, that's the importance. So I think like that's a huge kind of debate between the generator and the user. But as my experience at different COPs like Thea, we are part of different climate outlook forum. In fact, right now it's going on for the South Asia, and I have to wake up 2 a.m. today. So the point is, like, I really like Einstein comment, like, you have to be like explain simple way, but not the simpler way. Because if we make it like, as Thea said, making a pie chart or something like that is very easy to understand, but doesn't mean that what we want to explain, they understand the same point. So I think like the capacity building from the user perspective is so important. That's why we do a lot of training of the trainers, like how the agriculture extension officers explain the forecast map to the farmer if he doesn't understand the maps. So I think like there's no simple way that this is the map, use it. Rather, to understand how to interpret the map is so important.
John?
I would just add to those comments, and I would say that, the visualization of all things, subseasonal being one of them, is exceedingly important. Whether you're looking at platforms and how you visualize things on platforms, if there's general information out there, but yeah, and the end user having input from that, and making sure that the right communication is getting to the end user, again, so they can be more informed or make decisions here overall, exceedingly important. And the end user, it almost like should start there overall as to what their needs are, first, and then we go from there.
Mary Beth?
The only thing really I have to add to those comments is from an impact standpoint, knowing the added impacts to an event, for example, a hurricane or a cyclone, often are used in categories, but there's wind, tornado, storm surge impacts from these. And so there's stakeholders that are involved in the development of those tools to help make sure that the wider spread impacts are being conveyed to the public beyond just the canonical sort of usages that we've had.
Great. So I'm gonna comment on this as well. I think, right, we have 4 panelists and myself. I'm pretty sure that we eat, breathe, and sleep on subseasonal forecasting, right? And so we all love the science, but in the end, we're all involved because we want to help people, and we want to help businesses, and we want to help organizations. And within those organizations are the stakeholders. And so just like the observational data is absolutely critical to the forecasting, the stakeholder is absolutely critical to the application of the information. And so without stakeholders being deeply involved in the final creation of the product, it's unlikely that the subseasonal forecast and the science of it is going to be very, very valuable. So my experience anyway is that customers and end users and stakeholders they're absolutely critical to help frame and rephrase or repackage the information that we are all working so hard to create. So I think with that, I'm going to bring the webinar to a close. Again, let me thank each of the panelists. We have people from Singapore, we have people from Europe, and we have people from the United States on the webinar, and it took quite a bit of logistics to pull off all the time zones. So thanks everyone for doing this at odd times, especially you, John. If you have questions that you'd like to ask the panelists some, right at the end here, there will be a contact information of Ian Harper, who's helping us produce this. You can email your questions to Ian, and Ian will distribute the question to the panelist that you're interested in having your question. This webinar was recorded and will be available in the near future. Everyone who registered for the webinar will get an email letting you know where you can watch the webinar again. And looking ahead, there will be more InterMET.digital webinars. And again, we will communicate to you future events via email as well. So to conclude today's proceedings, it's goodbye from our panelists, Mary Beth, Thea, John, and Nachiketa, and me, Jan Dutton. Thank you very much, and hope to see you on the next webinar.
Thank you, Jan.
Thank you. Thanks, everyone.
Thank you
For having us.